last but not least, the fifth one, the last one, is going to be delivered to you. The lecture is entitled Electromagnetic Hiding of the Plasma Patch Antenna for the Military LEO Satellite. What you might be wondering, what use or what advantage a plasma antenna for LEO satellite. Uh, but this application includes CubeSat Light too. Military people are intrigued by the use of drone groups and cube satellites. So cube satellites, which can be destroyable after being finished with their mission, that's their target. By the way, they do not like to be recognized by the enemies. They are just entering the border or some territories they have is off limits. So plasma antennas, when it is turned on, it works as a metallic structure. But when you turn off, like what now what they are LED lights, but usually we had an incandescent light. Incandescent lights mean 형광등. So when incandescent lights were turned on, they seem like the ion beams work as kind of a metallic path. But if you turn the incandescent light, actually it seems like just a cylinder, empty cylinder. So electromagnetically, they can get transparent when they turn off the plasma patch or plasma antennas. Um, so people might be able to find the applicability of plasma antennas. I know plasma antennas still haven't weighted their fields into a lot of areas, just confined to just a theoretical or experimental approaches. But 2 years ago, one person from research of what atomic, what I forgot the name, Korean Institute of Atomic Research, Atomic Energy Research, they visited me to write a proposal, which was not finally not accepted to the military, but they suggested to me, Professor, what about just designing the plasma antennas, which work for satellite applications or radar applications? So that was the motivation. We just launched this project. The motivation was already mentioned by me just a minute ago, but it's going to be elaborated on again. And background and previous works are going to be shared with you. And satellite communication antennas, they're EM invisibility. EM invisibility, there's an EM transparency. We can see and we can recognize the existence of an incandescent light or plasma antenna with our naked eyes. So optics can find plasma antennas, but electromagnetic energies coming all the way from the radars cannot find them when they are turned off. So it is a kind of a EM invisibility. So, when these EM invisible antennas are used for satellite communication, what we have to do is we should tune the frequency of operation to what satellite developers are interested in, and the size of the antenna should be quite proper for the placement on the top or one side of the satellite box. Firstly, my students put the pictures of satellites. Yeah, as you saw, this picture is quite popular in people's referring to in terms of introduction to what CubeSat light looks like. So this is the one, and as you see, 1, 2, 3, 4 on on each of the top and bottom sides of the satellites are deployed to have various functions. So they can increase the diversity gain by having 8 antennas. But the problem is the cost. So if you want to add one set of four antennas compared to top to bottom, or from bottom to top, actually you have to have a discussion with the system guy or the funding organizations. If they give you the get-go, then you can go. But mostly they are quite skeptical about the placement or the addition of the other RF sensors. So you have to be particularly careful about it. And anyway, as far as the funder is rich enough to let you afford these antennas, you can design 8 monopoles, which are placed in the antenna. By the way, these antennas are made out of metallic structures. So if there are radars which have a very high sensitivity, shine the electromagnetic wave energy impinging on the surfaces of the metal body of antennas, actually they can be easily detected. The radiated scatterers radar cross section is called RCS. Excuse me. RCS. This RCS, the larger the RCS, the higher probability of being detected by the radars on the ground. So CuBe, as I told you, CuBe satellite flies or hovers over you by 800 kilometers. It's just really far. From here to Ulchin, how far is it? Around 300 kilometers? Around. For 800 kilometers, let me think, from here to Jeju Island or Yeodo or Kyushu, around 800 kilometers. 800 kilometers, UHF with the even 20 milliwatts can detect the things if you have a long range radars. Before CuBe, it can be detected, but mostly detected by its body, not like antennas. Antennas quite shallow or very thin, but the structures, the sizes of the bodies of satellites are quite enormous compared to the sizes of or RCSs of the 8 monopole antennas. But anyway, we try to reduce the radar cross section. That means we make an attempt to reduce the probability of being detected as a target. Anyway, we can put absorber, metamaterial absorber here. Metamaterial absorber shows you, this is the graph or view graph, which looks like a bandpass filter. The y-axis or ordinate, its name is what? Absorption rate or absorptivity, 흡수율. This metamaterial is absorber. So you can hide your structure with the metamaterial. This was designed by us a number of years ago. We tested and we simulated and tested. It works. This tells you almost 100% absorptivity is found from 6 gigahertz up to 14 gigahertz. So I'm giving a question to my student, Changyang. This frequency is good for satellite communication or not, especially military. Okay or not? Okay. Because military adopts the C-band, S-band, L-band before radars or satellite communication, X-band, which start from 8 gigahertz up to 10 gigahertz, and 10 to 12 gigahertz, it's called the Ku band. So these frequencies are just easy money for satellite communication people for military. By the way, we can use what metamaterial approach, but this is what expensive or the size matters. So what we can do is, what about the plasma antenna? But plasma antenna also still is quite pricey. We can guarantee whether the space project will be successful or turn out to be failure when once they adopt the metamaterial the plasma antennas. But we cannot stay at one position. We should move on, keep marching on for the new project or new challenges. Yeah, this slide shows you what metamaterial behaves like. So as you see, when we have a metamaterial structure like this, we can twiddle the epsilon r and the mu r. Actually, technically speaking, epsilon r, mu r here are effective permittivity and effective permeability. We don't change the materials, but we change the effective epsilon r and effective mu, which are calculated from S11 and S21 are reflection coefficient and transmission coefficient. We can see the representative characteristics of metamaterials from this 4 quadrants of constitutive parameters of material. When we have a negative mu and negative epsilon material or hosting media, not by changing the authentic material characteristic, but by changing the effective permittivity and permeability by giving some specific metal patterns and the layers or configurations of stacking, things like that, we can make Drude model material and Lorentzian model material. When they are combined together, so-called epsilon negative and the mu negative, we can make this very interesting but unprecedented phenomena. Why? As you see, this is a metamaterial part. Mu and epsilon at the same time are below 0. Here, air, the air of the waveguide, and this is the real air, the free space. So it has a refractive index positive in the air of the waveguide, but negative refractive index coming from epsilon negative and mu negative. As you see, wave coming back, but actually energy goes from left to right without distortion. Energy propagates from left to the right in the overall picture. This is what metamaterial gives you. Here, energy seems to travel back, never. Only phase of the electric field tries to go back or like a moonwalk, but the energy propagates accordingly or according to the direction of the propagation in the air of the waveguide. So here, energy propagates without any distortion. So here, you can see, usually, if this is a positive refractive index material, energy goes to this direction. Can you see this cursor here? Can you see how my cursor moves? cursor 움직이는 거 보여요? 아, 그렇구나. When you have this is called a prism. When energy is injected from left to right, this prism slab is filled with the negative epsilon and negative mu. Energy goes this, and finally, right after the interface between the prism slab and the free space, energy is not refracted to that direction. This occurs in the usual right-handed material, but here left-handed material takes the energy propagation to this direction. This means 자, 굴절율이 양수가 아니고 음수다 이런 얘기예요. So if you learn optics, especially ray optics, ray 광선 이거 끊는 걸 해보면 양수가 되면 이렇게 가야 되는데 얘가 이렇게. So this shows you the one of the flagship features of metamaterials. Anyway, plasma is located here. Where? Here. Epsilon negative material. Epsilon negative material. So when you turn on the incandescent light, the metallized ion beam occurs. Why? It is epsilon R negative. But if you turn it off, actually just free space, kind of what vacuum. Inside it is a vacuum, right? Vacuum is what epsilon is positive. So it behaves like an air. So the radar signal cannot is not reflected by it. But if you turn it on, actually the metallized part, which comes from epsilon negative or negative epsilon. How can you make it? Actually, you can ask the physicists who work on the plasma physics. But we can understand that like a Townsend, the ion, what chain reaction like that. Townsend ion 그 이제 2차 반응 이런 것들 공부를 하면 알게 됩니다. By the way, plasma can be used. Yeah, can be used or may be used, but I cannot say it must be used. Thinking about or taking into consideration of the price we have or we are given, what if that is out of our budget, we can't do it. By the way, why not enjoying the theoretical approach? Yeah, here comparison of matter state, solid, liquid, gas, ionized plasma. Ionized plasma moves. The particles are moving freely. So actually the density of the vacuum or a density of the inside of what just enclosed or airtight cylinder of the incandescent light is a gas. Gas is what? Density is very low. But when you turn on ion beam, that means it moves very fast. Moves very fast. That means it makes a kind of a bridge. You know, Altair and Vegas, 현우직녀, they meet through what? Crows and magpies. They make the bridges. So they can walk on that, right? Walk on the bridge. Kind of just a very temporal bridge. It soon disappears, by the way. So very fast moving ions make kind of a free electron path. So it works as a metal. So that's the explanation of the plasma working as a metallic bridge or metallic media like that. But we are not the plasma physics people. We just use them. So here we consider only two states, what on off like that. But you might be confused, or Professor Gang goes back to the original or the waveguide structures. No, I'm going to change. How? These waveguide structures, the metal parts are going to be replaced by what? Incandescent light cylinders. 우리 형광등으로 바뀌게 돼 있어. How? 이렇게 다 형광등이야. 형광등, 수수깡 같은 거 있죠, 여러분들. 수수깡 같은 거. If we can afford the manufacturing of this highly or densely populated arrays of plasma cylinders, we can do. But are we the only people who think very strange thing? No. In America, in the United States, Navy not Air Force, Navy and Army already have tried the adoption of the plasma antennas before, and still, but everything kept in secret. We do not know. The only thing we can approach is some academic or theoretical papers or articles, but these papers do not reveal everything on it. Just what low-level or small-scale details on it. But this is the first approach. Horn antenna, like an array antenna or slot array antenna, a variety of approach, or patch antenna. So if I comply with the title I already gave you for this talk, we had to open the talk. I had to open the talk with this picture first, but I'm already I'm ready with a sufficient number of examples for plasma antennas. So waveguide mode, TE10 mode. So students from Soonchunhyang University, along with my students who are aware of waveguide theories, you know TE10 in the rectangular waveguide, they are the dominant. It is a dominant mode. But if you have a conical horn, you have to change from the TE10 to like a HE1 mode, like that, hybrid mode. What is a kind of what just out of the scope of this topic. But anyway, it is worthwhile to learn. It is worth learning waveguide theories. Very beautiful. I handled waveguides a lot of times in the past. That was my field of specialty when I worked for Hanguk 전자통신연구원 or Electronics and Telecommunication Research Institute. By the way, so the frequency should be at least above 8 gigahertz here. Why? X-band is one of the cup of teas. 여러분 영어 표현 알죠? cup of teas. 뭐야? 즐겨하는 거. It's my cup of tea. 이렇게 해주면 즐겨하는 거. Military cup of tea for satellite is 8 gigahertz or 10 gigahertz, like that. So here you see the reflection coefficient of this antenna system. But this happens with the full metal body or the solid metallic structure. 완전히 금속으로 된 거. 단단한 거 있죠. So field distribution, electric field, T10 mode in the aperture, the final end of the horn antenna. Sorry, here. Starting point. When, because as I told you, the standard to see the antenna or impedance matching is well done for the structure is S11 less than minus 10 dBs, right? Usually, but in the waveguide structure fields or world, minus 20 dBs sometimes. Very harsh. Very harsh. Why? You have to send your signal over 800 kilometers or 320,000 kilometers. So any little attenuation is not acceptable. That's why. So far field pattern of the horn antenna from the metallic solid antenna is this. But we can replace the surfaces of the horn with this cylinders of a plasma cylinders. So plasma cylinders, very narrow plasma cylinders. You can also make this one line. You have seen the neon sign, right? Meander the neon sign. So the neon or incandescent structure can be also used here if you can. But you should spend a lot of money to let the glass maker to just blow it to form it. That's why we have to spend a whole lot of mucha mullah. Yeah, then minus 10 dBs. Yeah, the S11 is degraded or deteriorated by introducing the cylinders. Why? As you see, 울퉁불퉁. Looks like the railing of the what is it? There's a staircase. So railings give energy leakage, and the ultung or very wiggly and rough surface for the waveguide, then impedance match changes. But what for from the standpoint or standard of a real horn antenna, it is not acceptable, or I'm not happy with this. But as a new approach or experimental approach, it is quite acceptable. So TE10 motors, well kept. This is electric field pattern at the aperture of the rectangular waveguide, and this is a magnetic field. This is an electric field and magnetic field. They are very similar to each other. And if we turn our attention to far field patterns, they're very similar from as what three-dimensional far field patterns. So these are 2D plots of the horn antennas. And we were not just staying there. We tried another attempt or efforts to make them as array antennas, 1x4, 2x2, 1x4, 2x2. This is metallic structures. These are the plasma cylinder filled horn antennas. So beam can be tilted also. We assume different phase sets to steer the beam. So you can see 1, 2, 3. Here 1, 2, 3. Here 1, 2, 3, 1, 2, 3, 4, 5. Yeah, you can make 5 beams, but here the beam steering capability is a little just disappointing compared to the real one, but you can approach. So this is the take-home work you have to challenge. And the slot array antenna, from the metallic solid structure to the plasma cylinder filled one, return loss, the quality factor has changed to a worse direction, but we still can use it. And we increase the number of the elements. It is unavoidable to have a elongated or size increasing phenomena here. And the far field pattern looks very sharp compared to these ones. And finally, you can see the patch antennas. But here, the patch antennas, I do not use the what is it? A substrate. A substrate, dielectric substrate. We only use the air substrate. Why? Air substrate can also reflect the signal from the ground, so they can detect us. So air and patch, but we only need the kind of bolt or supporting structure to hold it in the in the air. And the metallic ground is also replaced by what? Plasma cylinders. So everything here is the plasma cylinder. So the only thing, the coaxial feeding, this should be metal. But as a sticking out structure, RCS cannot detect it easily. That's the thing. Why? They are anti-parallel in terms of the direction. But when they are perpendicularly oriented, detected very well. Signal incoming and impinging it, reflected back. That's why. Here, coaxial cable, the orientation of the coaxial cable is the direction of the incoming wave. So we are not worried about the bad effect. So here, S11 is good, and far field pattern is almost the same as that of solid metal type. And we extend this to 1x4 and 2x2 arrays. Here, we can steer the beam 1, 2, 3, 4, 5, 5. If you give different phase sets underneath, you can change the direction of the beam. And also 2x2, this is the best 2x2 array can do. Chang'an, right? So we have reached the conclusion part. Yeah, electromagnetically transparent antennas are well tried, and from the motivation, on the basis of the motivation of one research institute for defense application, and plasma. The characteristics of plasma briefly were mentioned, and the simple antenna theory was introduced to you, and EM invisible antennas were given with the data. Actually, they are not measured, but they are simulated one. I believe, as far as we can find the right fund giver or fundraiser for the plasma antenna project, we can what experimentally implement it. Thank you. 아이고. 자, 질문 있는 분들은 나중에